You are welcome to another edition of our physics online lesson. And today we are going to be reviewing refraction of light. We have already introduced light and we have been able to also talk about reflection. So today we'll move into another property of light, which is refraction. I will go straight into it. Refraction is a change in the direction of a wave as it passes between media of different densities. The change in the direction of a wave as it passes between media of different densities. If light comes to the boundary between two surfaces, let's say this is a material and this is another material. Let us assume that both material 1 and material 2 are transparent, because that is necessary for light to even pass through them in the first case. If light is going to go through 2, and 2 is not like 1, in the sense that it differs in density. For example, if 1 is air and 2 is water, we all understand that water is denser than air. So if light is going to move through water, we expect its direction to change. The change in the direction as it moves between media of different densities is what I will refer to as the refraction. So clearly we'll say here that the light has been refracted because there is a change that has been caused to its path. When refraction occurs, there are other properties about the wave, the light wave, that are also affected. It is not only the direction that is affected, the speed of the light is also affected, and the wavelength of the light is also affected. In fact, when refraction occurs, the only thing about the light that is not affected is the frequency. The frequency before refraction will be equal to the frequency after refraction. But the speed before refraction will not be equal to the speed after refraction. In fact, the change in direction that is brought about is due to the fact that light will now have to travel, light naturally travel with different speed in different media. The speed of light in air and the speed of light in water are not the same. So because of that, when light travels through the two, there will be a change in direction that the change in speed is going to be impacted on it. The wavelength will also change. The wavelength that light, being a wave, will have in air will not be the same wavelength that it will have in water. And the change in wavelength, the change in speed that we have already discussed, and the change in direction that occurs to a wave due to the fact that it is moving between media of different densities is what is called the refraction of light. Refraction is also governed by laws. I will call those laws the first and the second law of refraction. Don't forget that when we were talking about reflection, we said that there are laws of reflection to govern the process of reflection. Also for refraction, we have two laws governing the process of refraction. Let us assume that this is the first medium. I would like to call this medium A. I would like to call this other medium B. If light moves through A in this direction, we are just saying that its path will be refracted through B. Its path will change through B, and that is the refraction. The light that comes to the boundary between medium A and medium B, I'm going to call it the incident ray. And that is the same light, that's the same name that we'll use to refer to the initial ray of light, also under reflection. But this time we don't have reflection. This other ray of light that comes out of that boundary that shows that the light has been refracted is called the refracted ray, as opposed to reflected ray that we use under reflection. Now the point where the incident ray meets with the surface or the boundary between the two media is called the same name as earlier used under reflection. It will be called the point of incidence. Now, if I draw a line through the point of incidence, making 90 degrees with the surface, I already gave you the name of this line under reflection. Its name remains the same, and I'll call it the normal. It is not a ray of light, and that is why I'm using a broken line to represent it. Let us continue. From reflection, we know that the angle between the incident ray and the normal is the angle of incidence. So this is the angle of incidence, and the angle between the refracted ray and the normal is called the angle of refraction. I'm also going to represent that with R. So R in this case is just the angle of refraction, and that makes it completely different from the angle of reflection that we have earlier referred to. So these are the terms that we are going to use under this. Now we talk about the laws of reflection. Reflection has two laws. The first law of reflection states that the incident ray, the refracted ray, and the normal at the point of incidence all lie on the same plane, just as we have said for reflection too. The plane that has the incident ray will also be the plane that will have the reflected ray, and that will also be the plane that will contain the normal. So the incident ray, the normal, and the refracted ray at the point of incidence, all three lie on the same plane. So we can move on from there. The second law of refraction is also called the Snell's law. The second law of refraction is also called the Snell's law, and that law states that the ratio of the sine of angle of incidence, the ratio of the sine of angle of incidence, that means if I find the sine of the angle of incidence to the sine of angle of refraction, to the sine of angle of refraction is a constant for a given pair of media. Anytime refraction takes place, such that we now have an angle of incidence, we have an angle of refraction, we expect that when you find the sine of the angle of incidence and you find the sine of angle of refraction, as long as you have the same pair of media, it will always give you the same value. When they say something is constant, it means if those two items changes, they will change to the extent that by the time you find what is in that expression, it will still be the same thing. So anytime refraction takes place between a pair of media, let's say A to B, as long as it is A and B that are involved, when you find the sine of angle of incidence and the sine of angle of refraction, if you divide them, you will have a constant value. So that is what Snell's law is telling us, that the ratio of the sine of angle of incidence to the sine of angle of refraction is a constant for a given pair of media. The constant will be expressed as a ratio of what I like to call the refractive index of the medium. For both, we will refer to as the refractive indices of the medium. So I'm going to take a cut and I'm going to try to talk about refractive index of a medium. The extent to which a medium will refract light is a number that will be represented as the refractive index of that medium. If light has traveled through vacuum and it now passes through air, we expect air to refract it a little, to change its direction from what used to be its direction in vacuum. If light passes through vacuum and it suddenly comes into water, we expect water to refract it, to change its direction from what it has in vacuum. If light travels through vacuum and it suddenly comes into glass, we expect glass to also change its direction from what it will have in vacuum. The refractive index is now a measure of how much change in direction each of those media has been able to bring to light. And there are so many ways for determining the refractive index. We are going to try to talk about each one of them. If I want to find the refractive index of a medium, these are the formulas that I can use to find the refractive index of that medium. I can use the speed of light in air or vacuum. I will divide it by the speed of light in the medium. I can also use the wavelength of light in vacuum or air. The value that light has for its wavelength and speed in vacuum and air are very, very close, such that we can use them interchangeably to determine all of this. So the wavelength of light in vacuum or air divided by the wavelength of light in the medium. And lastly, I can use the real depth of an object all over the apparent depth of an object. I'm going to explain all of this because I told you that refraction affects the speed, the wavelength, and the direction of light. It means that I can use those properties that are affected by refraction to determine the refractive index. And one of such is speed. If I need to find the refractive index of water, for example, all I will look for the speed of light in air. I'll divide it by the speed of light in water. If I want to find the refractive index of glass or even water, I will divide the wavelength of light in vacuum or air by the wavelength of light in water or glass. Now, the third one, I can also use real depth of an object in water all over apparent depth of an object in the medium, because we understand that refraction gives the first impression of the depth of an object. If I put an object inside a cup of water, by the time I look through, it will appear shallower than it is. It will appear as if it has been displaced upward than it is normally. That change, that upward movement of the object, that apparent upward movement of the object, I use the word apparent because that object has not been actually displaced upward. It only appears to me as if it has been displaced upward because of the refraction process that is going on. That change in depth, that apparent upward displacement will give me a change in depth that I can use to find the refractive index. So the refractive index, I would like to represent how the change in depth can be possible. If you place an object in water, let us say the object is placed in water at this point A. We expect that for me to see the object above the surface of water, for you to see any object, that object must send rays of light to you. That object must send light to you. When the light gets to the boundary between air and water, we expect it to be refracted. So what I am actually seeing is the refracted light coming from that object. Like I said under reflection, I said our eyes are known to believe in rectilinear propagation of light. So while the light that is coming to my eye is actually the refracted light, whose direction has changed from that of the actual light that is coming from the object, my eye will have an optical illusion that will make it believe that it is coming from a straight point inside the water. So it is going to see the object not at this point, but at B, where it believes that the light that is getting to it is coming from. So this creates two different depths. While the object is here, I am actually seeing it here. So where I'm seeing it from the surface of the object, from the surface of the water is the apparent depth, and where it is from the surface of the water is the real depth. The real depth. So the refractive index, therefore, can be obtained when I divide this real depth by the apparent depth. It is not just a phenomenon that is common with water alone. It is common with all materials that allow light to pass through them. If you drop an object under glass and you look through the glass, it will appear to have been displaced upward. The difference between the real depth and the apparent depth must be the apparent displacement. This difference between the real depth and the apparent depth will be called the apparent displacement. So the apparent displacement is not the real depth, it's not the apparent depth, it's the distance through which that object has been upwardly displaced. I can use it to find either of the two if I know the other. So with all of these are the formulas that we can use to find the refractive index of any medium that we need to use. We now from there go back to what we said under Snell's law. Snell said when a ray of light is moving from a medium A to medium B, by the time we find the sine of the angle that the incident light is making, and we divide it by the sine of the angle that the refracted ray is making, it should give us a constant. Let me tell you here and now that constant can be expressed as a refractive index of the second medium all over the refractive index of the first medium. So the constant that Snell said the ratio of the sine of the two angles must be equal to will be equivalent to the refractive index of the medium where refraction is taking place all over the refractive index of the incident medium where the light is coming from. So if this were to be going on between water and glass, let's say the light is going from water to glass, we are saying that the sine of angle of incidence, the angle of incidence will be in water, all over the sine of angle of refraction, the angle of refraction will be in glass, must be equal to the refractive index of glass all over the refractive index of water. The refractive index of glass all over the refractive index of water. So with all of this, we have been able to explain how to find the refractive index for any medium and how to use them to solve a refraction problem. I'm going to take an illustration of how that can be done. I'll try to take one or two questions, then we'll move on in our study of refraction. The first example for today, we are told that the speed of light in air and glass are 3.0 times 10 raised to power 8 meters per second and 1.8 times 10 raised to power 8 meters per second, respectively. The speed of light in air, and the speed of light in glass must be 3.0 times 10 raised to power 8 and 1.8 times 10 raised to power 8. 3.0 times 10 raised to power 8 meters per second and 1.8 times 10 raised to power 8 meters per second. If the angle of refraction of a ray of light incident on an air glass interface is 30. We now have light that came to the boundary of air glass. That means the light is going from air to glass. We expect it to be refracted. We expect it to be refracted to change direction. We are told that if the angle of refraction of a ray of light that is incident on air glass interface, the angle of refraction is 30. The angle of refraction will be the angle between the refracted ray and the normal. That's 30 degrees. The angle between the refracted ray and the normal, which is 30 degrees. We are asked to find the sine of the angle of incidence. Number one, how do I even know that the incident ray will be in air? We are told in the question that the ray of light is going from air to glass. So where it is coming from, that's where the incidence will be. And where it's going to, that is where the refraction angle must be. So I want to find the sine I. The very first thing is I'll try to write out the Snell's law for this problem. The Snell's law for this problem should be sine I all over sine R is equal to a constant. And I told you the value of that constant. Don't forget, I said the constant will be the refractive index of the second medium all over the refractive index of the first medium, and the first medium is air. So I can rewrite this as sine I all over sine R is equal to refractive index of glass divided by the refractive index of air. But before we move on, we need to know the refractive index of glass and the refractive index of air. That is where you are going to need all of the formulas for refractive index that I wrote down earlier. The refractive index of glass will be the speed of light in air all over the speed of light in glass. So the refractive index of glass will be the speed of light in air is 3.0 times 10 raised to the power 8 meters per second all over the speed of light in glass, and that is 1.8 times 10 raised to the power 8 meters per second. If we divide them, we should have 3 divided by 1.8, and 3 all over 1.8 should give us 1.67. 3 all over 1.8 should give us 1.67. Should give us 1.67. I can also find the refractive index of air, but usually we just take the refractive index of air to be 1. If you want to find it from this formula, the refractive index of any medium, the medium now is air, will be the speed of light in air all over the speed of light in the medium, and the medium is also air. So you will observe that that should give us 1. Generally, for most questions, we always assume that air has a refractive index of 1, except we are otherwise stated. So if I put all of that inside this question, I should have sine I. My I is what I don't know, all over sine R. My R in this case is 30 degrees. My refractive index of glass is 1.67. The refractive index of air is 1. If you do that, you'll find sine I as, if you cross multiply, 1.67 multiplied by sine 30, which is 0.5. My sine I is going to be 1.67 multiplied by 0.5, and that is 0.833. 0.833. That is what they want me to find. If you want to proceed to find the angle of incidence, then you can easily just put the value and you get it. Now we continue with this. It is possible sometimes too for us to have more than a medium. We can have light traveling between 3 media. It can first enter through air, if it enters through air, we can continue that same motion through another medium, then can continue through another. Let us assume that this first medium is air, while this second medium is water, and the next medium is glass. You only need to show the arrow so that we know where the light is coming from and where exactly it's going to. You cannot solve problem on 3 media together at the same time. You have to take it 2 at a time. I have to solve for air and water, and I have to also solve for water and glass together. For example, this will be my initial angle of incidence, the angle between the incident ray and the normal. This will be my angle of refraction. Now, at this point, I'm having my first point of incidence and the first refraction is taking place between air to water. The second refraction will now take place between water and glass. This will be my second angle of incidence. I'll call that I2, while this will be my second angle of refraction, that is R2. This is I1 and this is R1. Now, I can solve the problem by first doing what I have here as sine, using the Snell's law here. That will be the ratio of the sine of angle of incidence to the sine of angle of refraction must be equal to the refractive index of water all over the refractive index of air. Because in this case, the refraction is inside water, and I told you when you are writing your refractive index, the ratio of your refractive indices, that of the refraction medium must be up, that of the incident medium must be down. So this should avail me the opportunity to find any one of these four if I know the other three. Once I get that, then I will now move to the second point of refraction. I will write my Snell's law equation there too as sine of the angle of incidence, which is now I2, all over the sine of the angle of refraction, which is R2. It must be equal to the refractive index of glass divided by the refractive index of water. Divided by the refractive index of water. And with that, I can now solve the problem that I have here. Now, the only connection between the two will be that if we use Z angle or alternate angle, as we have learned it in mathematics, we expect that R1 must be equal to I2. You can see that the two of them form a pair of alternate angle. So if I've been able to get R1, it automatically becomes I2. When I say I2, I mean the second angle of incidence. When I say R1, I mean the first angle of refraction. When light travels between two media, of course, if the two of them do not have the same density, one is going to have an higher density and one is going to have a lower density. The one that has the higher density will be referred to as a dense medium, while the other will be referred to as a less dense medium. Let's say we have two media, medium A and medium B, Medium A, let us assume that medium A is denser and medium B is less dense. In that case, we will say that the light is traveling from dense to less dense. While the light is traveling from dense medium to less dense, it can also travel from less dense medium to dense medium, please. It can travel across both directions. It can travel from dense to less dense. It can travel from less dense to dense. We only know that for each of those combinations, the behavior of light differs. And that is what I need to explain now. When light travels from less dense to dense, a very good example of less dense to dense combination is if it is traveling from air to water. Air is less dense, water is denser. So, how will light behave? I generally will tell you that light will always form a smaller angle in the denser medium. The denser the medium, the smaller the angle that light will form with the normal in that medium. The denser the medium, the smaller the angle. That means if light were to travel from less dense to dense, it will travel in such a way that it will have a large angle with the less dense and a smaller angle with the dense. So it is now, because it has a smaller angle in the dense, we will say that the incidence angle is more than the refracted angle. And why is this so? I said earlier that light will always have a smaller angle in the dense medium than in the less dense medium. So if this is the case, we will say that as light travels from less dense to dense, it will move closer to the normal. Because it has a larger angle here, it is farther away from the normal. Now it is traveling in a dense medium, we expect it to be moving closer to the normal. So when light travels from less dense to dense, we expect it to move closer to the normal. On the other side, if light travels from dense to less dense, if the light travels from dense to less dense, we expect it to have smaller angle in the denser medium and to have a larger angle in the less dense medium. And generally, this is how I want to represent it. So, because it is having a smaller angle in the dense medium and it's coming from the dense, it's having a larger angle in the less dense medium and it's going to the less dense, we'll say that light is traveling farther away from the normal. It was closer to the normal initially. Now, upon getting to the next medium, it moved farther to the normal. So this is a very good example of a dense to less dense combination. Is if the light is going from, let's say, glass to air, or glass to water, or water to glass. In all of those combinations, the first medium are dense, while the second media are that I've used in those combinations are less dense. So we can move on with that. Specifically, there are things we can do if light moves from dense to less dense. And that is what we want to discuss. If we increase, let us assume that this dense angle, there's an angle here, that's the angle of incidence, and there's also an angle here, that's the angle of refraction. Clearly, when light is going from dense to less dense, we have already established that it will move away from the normal. That means the angle it will keep with the normal will be different from the angle that it will keep with the normal in the less dense medium. The angle in the dense medium will be greater than the angle in the less dense medium. Now, if we decide to increase this angle by moving the ray forward, by moving it backward, we expect this to also increase. According to Snell's law, sine I all over sine R must always be a constant. That means anytime you increase I, R will also increase, though it may not be by proportional amount, but it will also increase to ensure that the ratio of the two will also still be equal. If you now increase the angle I, R will also increase. Increase I, R will increase. Increase I, we expect that R will increase. Increase I, we expect that R will increase. In fact, generally, because this is larger, this one will always increase by a greater amount than the amount that you have used to increase this. So if you continue that process, it is possible that you get to a point where the refracted ray, because it keeps increasing itself in response to your own increase of the incident ray, it is possible that you now get to a point where the refracted ray will get to 90. So that I can represent like this. The incident ray will still be smaller, while the refracted ray will have already increased itself to 90. If this is the case, we will say that the light, yes, it's still a refracted ray, but the angle of refraction now is now equal to 90 degrees. The angle of incidence, when the angle of refraction becomes 90, is called the critical angle. So the critical angle is the angle of incidence when the angle of refraction is 90 degrees. And it is only possible in a situation where the light is traveling from dense to less dense. If that is the case, it means because the angle in the dense must always be less than the angle in the less dense, it is possible for you to increase your denser angle to a point where the less dense angle will have increased ahead of it to 90 degrees. When that takes place, the angle of incidence will be called the critical angle. So the critical angle, if you want me to define it, is the angle of incidence in the dense medium, where the angle of refraction in the less dense medium is 90. Is the angle of incidence in the dense medium, where the angle of refraction in the less dense medium is equal to 90. Please note that and let us continue. Beyond that, we can now have a very strange phenomenon. If you now keep increasing the critical, if you increase the critical by the slightest amount, of course, this in response will also attempt to increase itself. In increasing itself, it will have to now move into the incident medium. Remember that the whole of this is the incident medium. If this is to move into the incident medium, it won't increase by any bit other than the fact that it will now become a reflected ray. When it is still at 90, the angle is critical. But when you increase that critical, the refracted ray will attempt to increase itself. The refracted angle will attempt to increase itself. When it increases itself, remember it will now move into the incident medium, the medium where the incident is. And once this light comes to the incident medium, the only thing that can happen there is a reflection. Refraction can only take place in the other medium. Now it is escaping into the incident medium. If it is to escape into the incident medium, it will just join the reflected ray directly, and it becomes a strong reflected ray. So it means that while the second medium is there, the light is not even passing through. So it is possible that you have an arrangement of media, one below the other, and there's no refraction. It simply means that the angle with which the light met or came to that boundary is greater than the critical angle. When it is greater than the critical angle, you don't expect any refraction at all, no matter the media or the medium that you have put here. What you will now have is just pure reflection, and reflection will always obey the law of reflection that states that the angle of reflection and the angle of incidence must be equal. If that is the case, we will say that the total internal reflection has occurred. The total internal reflection has occurred. The total internal reflection has occurred. So total internal reflection is the reflection of a ray of light between a medium and a medium of lower refractive index when the angle of incidence has exceeded the critical angle. The total internal reflection is a reflection of a ray of light traveling between a medium and another of lower refractive index at the boundary between a medium and another of lower refractive index when the angle of incidence has exceeded the critical angle. So total internal reflection will take place under two conditions. Under the condition that one, the light is traveling from dense to less dense. This can never occur if it is traveling from less dense to dense. Now, the second condition is that the angle of incidence exceeds the critical angle. If the angle of incidence is still equal to the critical angle, total internal reflection will not take place. What we'll have is that there will still be a refraction, but that refraction will have an angle that is equal to 90, staying around the boundary, now ready to escape into the incident medium, and that is total internal reflection. Now, there are ways by which we can restructure our equation at the point when critical angle is occurring. When critical angle is occurring, we can clearly say that, remember that sine I is equal to all over sine R, according to Snell's, is the ratio of the refractive index. It will be the refractive index of the less dense medium all over the refractive index of the dense medium. I said by arranging your refractive index as a constant for Snell's law, the refractive index of the medium that has your refraction must be on top, while the refractive index of the other medium, incident medium, must be below. So if this is the case, if I want to use this for a situation where the angle of incidence is still equal to the critical angle, I can replace the known values. I will be equal to C, R will be equal to 90 degrees, and that must be equal to the refractive index of the less dense medium all over the refractive index of the dense medium. And that should be sine C all over 1, because sine 90 is 1, must be equal to the refractive index of the less dense medium all over the refractive index of the dense medium. The refractive index of the less dense medium all over the refractive index of the dense medium. Let us assume that the less dense medium is air. If it is air, I can say that sine C is equal to, remember that the refractive index, if it is for air or vacuum, can be taken to be 1. If that is 1, it will be all over the refractive index of the other medium, which is denser. This equation can also be used to either determine the critical angle that will occur anytime you have a combination of a medium and air, or it can be used to even determine the refractive index of a medium if you know the critical angle that it will make, provided the less dense medium is said to be air. Provided the less dense medium is said to be air. So we'll take some examples. The examples are thus: we have a system this is air and this is glass. We are told that this is 90. This is a reflected ray. This is an incident ray. And this is a refracted ray. Now we are told that a ray of light is incident on an air glass interface, as shown above. If the reflected ray is perpendicular to the refracted ray, this is the reflected ray, it is perpendicular to the refracted ray, as shown. And glass has a refractive index of 1.5. Glass has a refractive index of 1.5. 0. We are asked to determine the angle of incidence. What's the angle of incidence? To find the angle of incidence, we need to indicate it first. The angle of incidence is the angle between the incident ray and the normal. That's the angle of incidence. This would definitely be my angle of refraction. Angle of refraction is the angle between the refracted ray and the normal. This must be my angle of reflection. Since I've represented refraction with R, I will represent the reflection with R bar. This is 90 degrees. Don't forget that this is the normal and the extension of the normal. So I can take the whole of the angle here to be 180. They are all angles on a straight line. One other thing I want you to know is this angle of refraction is the incident angle, because anytime reflection is taking place, angle of reflection and incidence are always equal from the second law of reflection. If that is the case, we can now take the sum of angles on a straight line. The sum of angles on a straight line must be I plus 90 plus R, which is the refraction angle. It must all be equal to 180. I'll take this to the other side. I can take the refraction to the other side. That means that I must be equal to 90 minus R. How did I get 90 minus R? 180 minus 90 minus R. So that becomes I is equal to 90 minus R. Or I can also say that R is equal to 90 minus I. Either of the two will still be fine. So I can now write my Snell's law. Now Snell's law is the sine of angle of incidence all over the sine of angle of refraction. Incidence is in air, refraction is in glass. It must be equal to the refractive index of glass all over the refractive index of air. The refractive index of air is not given because generally question wants us to take it to be 1. I said it should be 1 except where otherwise stated. So I can have sine I all over, instead of R, I can substitute for R. I can have sine 90 minus I is equal to refractive index of glass is 1.50. So I can continue. This becomes sine I all over sine of 90 minus an angle is the cos of that angle. The sine, in fact, that's the meaning of cosine. Cosine means the sine of the complementary angle. So 90 minus I is complementary to I. The sine of 90 minus I is always the cos of I. So that should be 1.50. Sine I divided by cos I should give us tan I. If that is tan I is equal to 1.50. We can therefore find I must be equal to arctan of 1.50. I must be equal to arctan of 1.50. Should give us 56.31. 56.31 degrees. And that is all for that question. We'll take another question. We are told that two rays of light which are equally inclined to the vertical emanate from a point below the surface of a pool of water. Water's refractive index is given to be 1.33 or 4 over 3. If the two rays are inclined to each other at an angle of 80 degrees in water, the angle between the two rays when they emerge into air is dash. We have surface of water, we have a point, and we are told that two rays of light emanate from a point below the surface of water. We are also told that the angle between them, between the rays of light, is 80 degrees. Please note, the two of them are also equally inclined to the vertical. If we draw a vertical axis through them, the two of them makes equal angle with the vertical. That's the meaning of they are equally inclined to the vertical. If the angle between them is 80 and they are equally inclined to the vertical, that means each one is making angle of 40 degrees with the vertical, right there below the surface of water. The whole of this is water. Two rays of light which are equally inclined to the vertical emanate from a point below the surface of a pool of water. The two of them are coming from water, and water has a refractive index of 4/3. If the two rays are inclined to each other at an angle of 80 in water, what will be the angle between them when they emerge into air? Now they are emerging into air. They are now moving into air. So for this, now please, I want you to check a slight difference from what we have been doing. We used to place the incidence up and the refraction down. But here, I hope you can see that the incidence is down and the refraction is going to be up. You can do either of the two. The arrow is what shows the incidence, not the order in which the media are placed. I can place a medium up, then the incidence can still be down, while the one up is, just check the arrow. And from the question, we are told that the rays emanate, they originate from a point below. So they are coming from below, and they are going to be refracted out. They are refracted out. This will continue its path. When this one gets to this point, it's refracted out. So this is the point of incidence. And that is it. So when we check this, I think we can use Z angle to solve this. We can use Z angle. If we use Z angle, I hope you know that this place will also be 40 degrees, while this will also be 40 degrees. So it is the angle of incidence because it's the angle that the incident ray is making with the normal. This is also the angle of incidence here, is the angle that the incident ray is making with the normal. So what I want to find now is the angle of refraction. I've drawn it to look larger than the angle of incidence because it is going from a dense to less dense. I expect that the angle in the less dense will be larger. So what I will do is to find this refraction, I will write my Snell's law. Snell's law is sine I all over sine R is equal to the refractive index of where refraction is. The refractive index of the medium that has the refraction, that's the refractive index of air, all over the refractive index of water. Not the refractive index of up or down. The refractive index of the medium that has refraction must always be up. The refractive index of the medium that has the incidence must always be down. So this will be sine, your I is 40, your R is what I don't know. Your refractive index of air, let's take it to be 1. That of water, let's take it to be 4/3. We can continue with the evaluation. We should have, if we cross multiply, we should have sine R becoming 4/3 sine 40. Sine R becoming 4/3 sine 40. That should be sine R must be equal to 0.857. 0.857. R therefore must be arc sine of 0.857. R must be equal to arc sine 0.857, which is 58.98 degrees. Now, the ray of light upon emanation from water surface has an angle of 58.98. So I expect you to know that here to it will have 58.98 because it is the same ray of light and the two of them are inclined equally and they are moving into the same medium. So the angle between them will be The angle between them will be the angle between this and the vertical between the vertical and this. So that angle between the two must be equal to 58.98 plus 58.98. The angle must therefore be 58.98 multiplied by 2, and that is 117.96 degrees, or approximately 118 degrees. And that is the answer to the question. We move on to refraction in triangular prism. We can have transparent medium made into the shape of a triangle. For example, we can have a triangular prism that is made of glass. We can have a triangular prism that is made of plastic, transparent plastic. We can have triangular prism that is made into some other materials that are also transparent. Light can approach the prism from one side of it. If when light approaches a triangular prism from one edge, there will be a structural difference between how we solve this type of question from how we solve the questions on plain rectangular prism. The major difference is if it were to be a rectangular prism, once the light comes to that surface, we can easily just draw the normal. This surface is meant to be horizontal, so I expect the normal to be vertical. But here, the surface is not horizontal, so the normal will not be vertical. The normal must still be drawn because this is the point of incidence, but it must be drawn in a way that will show us that this normal is still making 90 degrees. Normal must never lose its essence. Normal is a line that must make 90 degrees with the point of incidence. It must make 90 degrees with the plane at the point of incidence. With the normal, I can determine my angle of incidence. Incidence angle is always the angle between the incident ray and the normal. It must always be the angle between the incident ray and the normal. Of course, it can now be refracted. It will now be refracted because it is moving from air to, let's say, glass, another medium. So the refracted ray will be represented this way, and this must also be the angle of refraction. That must be the angle of refraction. If I know that angle of refraction, usually I'll be given the refracting angle. Refracting angle is not angle of refraction. Refracting angle is a property of the prism. It is represented with A. It is the angle on the face that is directly above the orientation of your refraction ray. So if I know this A, then I can continue my simplification of this problem. If I know A, then I can easily find this angle. Mind you, this is the normal. If this is the normal, normal must make 90 degrees with the face. The angle between the normal and the face at any point must be 90. So if the whole of this angle is 90, I expect you to know that if a part of that 90 here is R, this remaining part will be 90 minus R. If I know that to be 90 minus R, I will now consider this very small triangle. I'll consider this small triangle that has 90 minus R on one of its angles, A on the other. I will use that to find this angle. Once I add angle and angle together, I will subtract them from 180. That will give me this. Let me call this angle angle X for now. Now, as the ray approaches this other surface, if it were to be a rectangular prism, if it approaches the other surface, I said it earlier when we were trying to solve problem on 3 media. In a rectangular prism, light comes to the point of incidence. It has an angle of incidence. It is refracted to the opposite face with an angle of refraction. When it gets to this opposite face, it is going to attempt another refraction. It is going to attempt another refraction. Why did I use the word attempt? It may not go out because this time is going from dense to less dense. It is possible that if this critical angle with which it wants to live, if this angle that it wants to live with is greater than the critical angle, it will instead be reflected. We said that earlier. But let us assume that there will be a reflection. The second angle of incidence with which it wants to leave this prism can easily be obtained as R. I said it earlier, the two of them form a pair of alternate angle or Z angle. Whatever this R is, that's the I with which this object is trying to live with. So I can now get that, and I will get this from Snell's law because another refraction has just taken place at this boundary. I can use my Snell's law to get this angle of refraction. This angle of refraction can also be called the emergent angle. The emergent angle. We move on. Here, it is not also that easy. At this point, it is now attempting another refraction. So I will have to draw the normal. When I draw the normal, what I will do is, to find this angle. When I do that angle, remember that the normal will always make 90 degrees with the surface. We always make 90 degrees with the surface. We always make 90 degrees with the surface. So if I already know this angle to be x, I can easily find the angle here as 90 minus x. And that will be the second angle of incidence because it's not the angle that the incident ray, it is the reflected for this refraction. It is the refracted for this refraction. It is the incidence as it is now trying to move out. So this is the second angle of incidence. It is now trying to move out, and I can get the next angle of refraction from Snell's law again. The next angle of refraction, I will also call it the angle of emergent, the emergent angle. And that is how I will solve the problem through this rectangular prism. That's how I'm going to solve the problem through the rectangular prism. I can also be asked now to find the deviation. I've only been talking about the incident and the refracted angle, but there's also the deviation angle. Remember, we talked about deviation when we were looking at reflection. Let us assume that light comes to a particular boundary. If it comes to a boundary, at that boundary, if the light is refracted, let's say towards the normal, this is possible if it is moving from less dense to dense. The extension of the incident ray, if I choose to extend my incident ray in its direction, that is my line of deviation. In this case, the ray of light will have moved in this direction if it has not been refracted in this direction. So it means the process of refraction has actually caused it to bend away from its original path now to the refracted path. This difference, the angle through which it was made to turn, because refraction happened to it, is the angle of deviation. Mind you, the angle between the refracted ray and the normal is the angle of refraction. The angle between the incidence and the normal is the angle of incidence. So I want you to look at a mathematical principle that we can apply here. A mathematical principle that we can apply here. This and this forms a straight line. This and this also forms a straight line. So the angle here and the angle here must be equal. That means I must be equal to R plus D. My deviation will be obtained as incident angle minus the angle of refraction. Incident angle minus the angle of refraction. There are instances too where the ray of light will move from the incident It will move from the incident that is dense to a refracting medium that is less dense. We expect the angle to be far away from normal because we said light will have a smaller angle in the dense medium. Let's say its angle in the dense medium is I. It means the angle in the less dense medium will be R. If that is the case, let me show the line of deviation. Line of deviation is the extension of the incident ray. This time, the line of deviation is coursing through our refracted angle. Now, the angle between the line of deviation and the refracted ray is the angle of deviation, because this ray of light has been made by the process of refraction to move away from its original part to the part that is now represented by the refracted ray. This must be the angle that, if we use the mathematical principle that we used earlier, remember this is the normal, and this incident ray forms a single line. It means that the angle here, I, must also be the angle here, which is what I. So the whole of the angle from here to here can be represented as a refraction angle. It can also be represented as D plus I. D plus I. If that is the case, I can say that my D is equal to R minus I. Remember that earlier on, when we tried to look at how to get the deviation for less dense to dense, we got I minus R. Now for dense to less dense, we are getting R minus I. If that is the case, I'll just say that to get the deviation in rectangular systems, just do the absolute value between the difference, absolute difference between R and I, and that should be your answer. This is not that direct. The deviation here, to get the deviation here, you have to extend the angle of the emergent ray, you extend the incident ray. Where the two of them meet, that is where your angle of deviation will be. Where the two of them meet, that is where your angle of deviation will be. I'm also going to try to say more questions on triangular prism before we leave the topic. I will tell you how to obtain the deviation for a triangular prism using a bigger diagram so that we'll be able to show all of what is necessary for us to show. If a ray of light, of course, the triangular prism, we have an angle, a refracting angle A. If the ray of light comes in this direction, this is our point of incidence. We said earlier, we will draw the normal at our point of incidence. When we draw the normal at our point of incidence, that will help us to know what is our angle of incidence. Then we expect that the ray of light will be refracted. When it is refracted, we show the angle of refraction as the angle between the refracted ray and the normal. Because the normal must always make 90 degrees with the face, I know a path now from Snell's law. Of course, I can find I and R. I can find R from I if I know the refractive index of this medium. I will just simply use sine I all over sine R is equal to the refractive index of the medium. Let's say this medium is M, all over the refractive index of air. If I assume that it's coming from air, if it's not coming from air, I'll divide it by the refractive index of the medium where it's coming from. So if I know I and I know the two refractive indices, I can find R. When I know R, I hope you know that the angle here will be 90 minus R. So from this triangle, I can now take the sum of angles in a triangle to determine this. I called it X earlier. Let me still name it as X. So the ray is the refracted ray from this face is attempting to leave at the other face. So this is going to be the incident ray. I'll draw the normal. It's going to be the incident ray at this face. It's a refracted ray from here. So this is 90 minus x. If it is 90 minus x, because this is the normal, that 90 minus x must be the second angle of incidence, because it's not the angle between the incident ray. I call this ray the incident ray here. It is a refracted ray after this refraction. It's the incident ray here. So now it will leave. If this is the second angle of incidence, I can get the second angle of refraction. Let me call it R2. I can use the Snell's law again. Sine I2 all over sine R2 must be equal to the refractive index of air now all over the refractive index of M, because refraction is now in air while the incidence is in glass. I want you to note the change in the arrangement of the refractive indices. So if I know I2, I can easily find R2. If I now know R2, that is the emergent angle. If they want me to find the emergent angle, that is R2. But the question can now continue. I can be asked to find the angle of deviation. If I want to find the angle of deviation, I will extend the emergent ray inward and the incident ray also inward. I will extend the two of them inward. I will use broken line because there are no rays of light there. It's just all extensions are not rays of light. The angle between the two is this deviation. And everything that I need to find that angle is just mathematics. I want you to look at this end, I want you to look at one angle, this R2. Let us find its equivalent from vertically opposite angle from this other end. And this is it. This angle R2 must be my I2 plus this other angle Y. That other angle Y, please, is not X. X is from here to here. Y is from this horizontal line to this point. Y is expected to be less than X. So if I add Y and I2 together, vertically, the two of them are vertically opposite to R2. I remember I will have found R2 from Snell's law. I know I2 before finding R2. I'll subtract I2 from R2. That will give me my Y. That will give me my Y. I'll do the same thing here too. These two rays of light, the angle they form here, these two lines, the angle they form is I. On the other side, they will form this I also. This is it. So a part of that I is what I have been given as R. I can easily find the other part. Let me call it A. I will now take this triangle that has my deviation on its exterior. This triangle that has my deviation on its exterior, if I draw that out, I will have this as my D. I will have this as my A. I will have this as my Y. Then, I hope you know that there's a law that governs the behavior of triangle that says that an exterior angle is the sum of two opposite interior angles. My deviation must be equal to A plus Y. And that is how I'll be able to get deviation. It's a whole lot of activity, but if you take it one at a time, I'm very sure you'll be able to get it. There are now instances where we'll be told that the ray is minimally deviated. The ray is minimally deviated. That means that the ray has the ray was able to pass through the glass prism and it recorded the smallest deviation that is possible at that angle of incidence. It recorded the smallest deviation that is possible through that glass prism. For there to be minimal deviation, for deviation to be minimum, certain characteristics or certain properties must be obeyed in this triangle. And I'm going to tell you those things one by one. If it is minimally deviated, if it is not minimally deviated and you're asked to find the deviation, you must do all of these that I've just described. But if it is to be minimally deviated, number one, These are the things that I've explained. There will be an initial angle of incidence. There will be a refracted ray that will also serve as the incident ray for the prism. For continuum, I said this will be called the second angle of incidence, the second angle of refraction. This will be the first angle of incidence, and this will be the first angle of refraction. Let me show the angle, let me show the direction. And I said if you want to find, this is the refracted ray, A. I said if you want to find the deviation, you extend this, and you must extend this too. If the ray is going to have minimum deviation, D minimum, number one, that minimum deviation must be formed on the line of symmetry of that triangle. It must be formed on the line of symmetry. It must be formed exactly at the middle of that triangle. It must be formed on the middle line that goes through the triangle. So number one, D minimum must be on the line of symmetry. Number two, the angle of incidence, the first angle of incidence must be equal to the angle of emergence. E, even if you are not told, anytime you are solving a problem on triangular prism and the angle of incidence and the angle of emergence are equal, there is minimum deviation occurring at that time. An extension of that is for this to be equal, the two that we obtain them from, remember we obtain R from I will obtain R2 from I2. If I is to be equal to R2, R must also be equal to I2. R must also be equal to I2. So I can just, without trying to use too many letters, I can now just call this I and call this R. We are getting there gradually. Let me write the Snell's law that connects this I and this R. The Snell's law is sine I, don't forget, all over sine R must be equal to the refractive index of the medium all over the refractive index of air. Let us assume that this is air. To further reduce the number of quantities we are working with, let's say that the refractive index of air is 1. Let me write it out, then express it in another form. Sine I all over sine R is equal to the refractive index of the medium. Now, if we check, we'll observe that this place must be I minus R, because the angle that these two lines will form is the same angle they will form on the other side, and it's just the same too. Here too, the angle it will form on the outside must be the angle it will form on the inside. This will be I minus R. So we said that the deviation being the exterior angle of this triangle must be equal to the addition of the two opposite interior. So I can write it out as D is equal to I minus R plus I minus R. That means D is equal to 2I minus 2R. Please let us note that. Let us note that. If I now extend this R, and I also extend this R, the two of them, probably by the way of my drawing, the two of them should also meet on the two of them should meet on that angle of, on that line of symmetry. But let us assume that they are meeting on the line of symmetry. We will now try to look for relations that we can write for these two. We understand that the total angle in, if we take this triangle into consideration, the exterior angle here too should be 2R. That's the sum of the two opposite interior. The first triangle gave me D minimum. Now I'm getting 2R from this other triangle. Now I want us to look at a quadrilateral. This quadrilateral, this four-sided shape, 1, 2, 3, 4. Is four-sided. I want us to look at it. this four-sided shape, I want us to look at it. If that is the case, we can now add the angles inside the quadrilateral together. This is A. The whole of this is 90 because it's the angle between the face and the normal. The whole of this is also 90 because it's the angle between the face and the normal. Then I can find this angle X. If I know this angle X, this angle, okay, without even saying this is X, since this angle and this angle are on a straight line, I can call it 180 minus 2R. If we add all together, we should get 360 because that's a quadrilateral. If I add A plus 90 plus 180 minus 2R plus 90, I should get 360. That will be A plus 90 plus 90 plus 180 minus 2R should be equal to 360. So clearly I can say that A plus, if I add the whole of this, it is 360 minus 2R is equal to 360. 360 can be brought here. I will have A minus 2R is equal to 0. A is equal to 2R. If A is equal to 2R, I can say that R is equal to A all over 2 or half A. If that is done, I can now say that I can put that into this expression. If I do it, I will have the deviation, which is the minimum deviation, is equal to 2I minus 2R. And 2R is A. I want to find I too. That means 2I must be equal to D minimum plus A. That means I must be equal to D minimum plus A all over 2. That means I must be equal to half, open bracket, D minimum plus A. If this is my incident and this is my angle of refraction, I can invert this formula. Sine I, my I in this case will be half D minimum plus A all over sine R. My R in this case is half A, and that should give us the refractive index of the medium. So if I know the refractive index of the medium, I can find the minimum deviation of the light through it, as long as that light is coming from A. And this is the equation that we have to use. So with that, we have ended refraction through plane surfaces. We want to see refraction through curved surfaces. Curved surfaces are lenses. And what is a lens? A lens has two transparent surfaces with curved edges. Two transparent surfaces with curved edges. It could be made of any transparent material, but usually it's made of glass. We have two types of lenses that we are going to review. We are going to talk about a concave lens and a convex lens. A lens that is thinner in the middle and thicker at the edges is called the concave lens, while the lens that is thicker at the middle and thinner at the edges is called the convex lens. Convex lens will also be called the converging lens. Please don't mix this up with what we did under reflection. Under reflection, convex mirror was referred to as the diverging mirror. But here the convex lens is the converging lens, while the concave lens is a diverging lens. Is a diverging lens. And that is what we have. Now, we want to look at terms that we are going to be seeing under lens, or lenses for both of them. For a convex lens and for a concave lens. All lenses have what is called the optical center. The optical center is the center of the lens, and it is represented with capital letter C. Optical center is the center of the lens. It has a principal focus, and the definition of the principal focus is almost the same as what we saw under reflection, only that this time we will have the light ray is being refracted, not reflected. When we have a convex lens, which is also a converging lens, we have a concave lens, which is also a diverging lens. They both have their F on both sides, the principal focus on both sides of the lenses, the principal focus on both sides of the lenses. And the principal focus I'm going to define thus. Principal focus is a point on the principal axis to which rays of light that are parallel and close to the principal axis converge after refraction through the lens. That is for converging lens. The point through which they converge after refraction through the lens. If you have any ray of light that approaches the lens, when after passing through the lens, it comes through F. Any ray of light that comes through parallel to the principal focus will go through F. If it approaches from the other side, because one thing with lenses is ray of light can approach from both sides, since both sides are reflecting. So when ray of light passes through from the other side, it also converges through F. So we define F as a point on the principal axis to which rays of light parallel and close to the principal axis converge after refraction through the lens. For concave, when you have parallel ray of light through concave lenses also do not converge because they are diverging lenses. What happens is they diverge. They will not diverge as if they are coming from F. If you have parallel rays of light, they will diverge out, but diverge as if they were coming from F. If they approach from this side too, when they get to the mirror after refraction, they will pass through because refraction is taking place. When they get here, they will diverge. They will only diverge as if they are coming from F. They will diverge as if they are coming from F. So we define the principal focus of this type of lenses as a point on the principal axis from which rays of light that are parallel and close to the principal axis diverge after refraction through the lens. If we bring the two definitions together, we'll say that the principal focus of a lens is a point on the principal axis to which rays of light that are parallel and close to the principal axis converge or appear to diverge after refraction through the lens. The principal focus of a lens is a point on the principal axis to which rays of light that are parallel and close to the principal axis converge or appear to diverge after refraction through the lens. What are the rays of light that we use to plot images on the lens? We can use any two of these three that I'm going to give you. The ray of light that here is point C, here is point F, here is point F. One I've already given to you. Any ray of light that is parallel to the principal axis will converge through F upon refraction. Any ray of light that goes through C will pass through C undeviated. Any ray of light that goes through C at any point will pass through C undeviated. And the next one is the opposite of the first. Any ray of light that comes through F will go parallel to the principal axis upon refraction. That can also be obtained for a diverging lens. So what are the images formed by a converging lens? The images formed by a converging lens include depends on the position that the diverging lens, that the object is placed to the lens. If this is F, I want to represent a point with 2F. I want to represent another point with F and 2F. Yes, same point will be represented on both sides. Same point will be represented on both sides. What we will now have is the object can be between C and F. It can be on F. It can be between F and 2F. It can be on 2F. It can be beyond 2F. As we have done for reflection, I want you to check a video on reflection to understand how this can be done, but we are going to run through them because it's just basically all the same. Now, I want to draw for a convex mirror, for a converging lens, at 5 different positions of the object. This is my F, and this is my 2F. This is my F, and this is my 2F. 2F and F, F and 2F, 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 2F and F, F and 2F. So if the ray of light is put at between the lens and F, for a ray of light that is between F and the lens, for an object that is put between F and the lens, I beg your pardon, a ray of light that is parallel to the principal axis will pass through F upon refraction, and the ones that go through C will pass through C upon refraction. When you check the refracted ray, they are not going to meet on this reverse side. So what we do is we extend them backward. If we extend them backward, we are going to form an image. Now, because we have extended it, the type of image that will form is virtual. For lenses, virtual images are images that are on the same side as the object. If they are real, they will be on the other side of the object. Now, if it is placed at F, rays of light that are parallel to the principal axis will come through F, and the ones that go through C will pass through C. You will discover that when you extend them this way, or the other side, they will not meet. So when you put the object between F and 2F, rays of light that is parallel to the principal axis will go down through F. The one that goes through C will pass through C undeviated. So they will definitely meet. When they meet, you can now place the image. For 2F, rays of light that are parallel to the principal axis will come down through F. You need to show some accuracy with this, where you are drawing it to scale, and the one that goes through C will pass through C. If you have done that correctly, you should get an image that will be exactly on 2F. Rays of light, now let's do for the one beyond 2F. If it is beyond 2F, rays of light that is parallel to the principal axis will come through F, and the one that goes through C will pass through C undiminished. This is C. So I want to classify each of the image or images. Here I have a virtual image. Any image that is on the same side as the object is a virtual image. This image is virtual, the same image that we got for converging mirror when the object is placed between F and P. Is magnified, is between F and 2F. Here, it is at infinity, so we take it to be real, magnified. Here, it is real, any image that is on the other side of the object in a lens. If it's on the same side as the object in a mirror, it is real. If it's on the other side of the object in a mirror, it is virtual. But for a lens, if it's on the other side of the lens, it is real. If it's on the same side of the object, it is virtual. So here, when you place the object between F and 2F, it is beyond 2F, it is magnified, it is real, it is inverted. When you place it on 2F, the image will also be on 2F. It will be of the same size, it is real. When you place it beyond 2F, when the object is beyond 2F, you get an image that is diminished, it is real, it is inverted, and it is between F and 2F. Please find time to review all of this. For diverging lens, which is a concave lens, we can also plot the image. We can also plot the image for diverging lens. This is your F, this is the 2F, and this is your F. On the other side, this is 2F. Anywhere you place the object, if you place the object at any point, and you draw your rays of light, mind you, the rays of light we are using here, any ray of light that is parallel to the principal axis, we said it will diverge, but it will diverge as if it were coming from F. And the one that goes through C will pass through C undiminished, undeviated. Of course, where the two refracted rays meet is here. Yes, a refracted ray goes through this point, and an extension of the other refracted ray goes here. So this is the image. This image is diminished, it is virtual, the same image that was produced for diverging mirror. Only that now this is a diverging lens, I will call it a concave lens. A diverging lens, I will call it a concave lens. So for all positions of the object for this lens, this is what you are going to get. So we'll say that a diverging lens produces an image that is diminished, it is virtual, and that is for all positions of the object. All of these are things we can use equation to get. We'll use 1 all over F is equal to 1 all over U all over 1 plus 1 all over V. That should be, we'll use it with the magnification, which is V all over U. We have said a lot about the use of this formula. When we're doing reflection, we'll just bring everything back into this. F is negative for a diverging lens. That's a concave lens. It is positive for a converging lens. That's a convex lens. But if F is not given, please leave it as F. By the time you solve it, you will get the positive or the negative as the case may be. V is positive for a real image. It is negative for a virtual image. But if V is not given, please note that you leave it like that. By the time you solve it, you get whatever it is that you need out of it. So the magnification is V all over U, and we can use this formula. Here it will be called the lens formula. When you are using it to solve for mirror, it was called the mirrors formula. Now we are going to check some applications of lenses. Lenses can be used to make microscope. And under microscope, there are two types. We have what is called the simple microscope and the compound microscope. And they can also be used to make what is called the telescope. From the diagrams, from the ray diagrams that we have, you will observe that when we place the object between When we place the object between the lens and F, between the pole of the lens and F, this is a pole, between the pole of the lens and F, we obtain the image that can be represented thus. Any ray of light that is parallel to the principal axis will go through F, and any ray of light that goes through C will pass through C undiminished. If we extend them, they won't meet on this side, so we extended them backward. If we extend them backward, they will meet, and we can put the image there. You will observe that the image here is magnified, and that is the essence of a microscope. When you bring an object close enough to a lens, a converging lens, a convex lens, it's going to form an image that will be magnified and is virtual, so we can see it. When the image is virtual and is magnified, we can see it. It satisfies the essence of a microscope, and this is called a simple microscope. So a simple microscope makes use of a converging or convex lens to form a virtual magnified image of the object when the object is placed between F and the lens. Meanwhile, there are instances where this may not be adequate. We might require a magnification that is even more than what the single lens can give. Then in that case, we make use of two lenses. We make use of two lenses. And we get what is called a compound microscope. Initially, we have a lens of short focal length. Let us say this is F, and this is 2F. This is F, and this is 2F. If we place the object between 2F and F, we will expect this type of image. One that is magnified, but it is real. So what we have is, we have a lens that will produce a magnified image of the object at a point beyond 2F. If I now decide to bring another lens close to this lens, if I decide to bring another lens close to this lens of longer focal length, another length of longer focal length, because the lenses are going to be different, let me use O, 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 O for this. This is called the objective lens. It is the objective lens because it is the one that is closer to the object. It has magnified the object to a point. I now want to use another lens. I want another lens to now work on the image of this object for further magnification. I want this one now to also magnify the image that we have. This will be called the eyepiece because this is what I will now have to look through. This is the eyepiece lens, or just the eyepiece. Now, I'll bring it close enough so that the image of the first lens, which is going to be the object of the eyepiece, will be between the eyepiece and its own F. Let's say the F of the eyepiece is here. Let's say the F of the eyepiece is here. F of the eyepiece. So now the eyepiece is going to work on this image. I will expect that there will be a ray of light that is parallel to the principal axis and it will pass through F. There's one that will go through C undeviated. If we extend these two, because they will not meet in this direction, if we extend them, they will definitely meet on this direction, and wherever they meet, that is where the final image will be. And that final image must be a virtual image. So, and it must be very big. So what we have here is that we have an object that has been magnified first by the objective lens to produce a real image that is magnified. Where are we going to place it to form a magnified real image? At the point where it is between 2F and F. It will form a magnified real image. Why must it be a real image? It must be a real image because it is only a real image that can be acted upon by another lens. It must be magnified because the purpose of this system is for magnification. So this will magnify it and make it real so that this can now work on it and also magnify. This one can now produce a final image that is virtual for us to see. When you use two lenses to form a much bigger image, what you have done is called the compound. What you have used is called the compound microscope. Compound microscope has two lenses. One is called the objective lens. That's the one that is closer to the object. And it has an eyepiece. That's the one that is closer to the eye. Generally, both of them are of very short focal length, except for the fact that the focal length of the objective is even smaller than that of the eyepiece. It's shorter than that of the eyepiece. We are going to see one question or compound microscope later. Then we'll move on into astronomical telescope. Telescopes generally are used to bring objects that are far away to view. If an object is so far away from you that you cannot see it, if you use a telescope, you will definitely see it. A very good example of a telescope that we are going to talk about is astronomical telescope. Astronomical telescope also makes use of two lenses. One is called the objective lens, as in the case of the compound microscope. The other is called the eyepiece, as in the case of compound microscope. The only difference is the objective lens now has a focal length that is, now greater than the focal length of the eyepiece. Under compound microscope, the focal length of the objective is less than the focal length of the eyepiece. So here we don't need to show the object because telescope wants to work on an object that is far away from you. So we'll just show rays of light coming from infinity. When they come from infinity, they will form an object. Can make them come anyhow. When they come from infinity, they will form an object at F. Wherever you can form the object, you can just call it your F. This is your F of the objective, and this is where the initial image will be. That's where the initial image will be. What we now want the eyepiece to do is for the eyepiece to form a final image that we can see. This is a real image. We want the eyepiece to come in so that it will now form a virtual image of what we already have, so that it will become visible. We bring the eyepiece inward as possible. This is the eyepiece. The image that has been formed by the objective lens will now automatically become the object of the eyepiece. And in that case, it means the object, which is the image of the objective lens, must be between the eyepiece and its FE, and its focal length, and its principal focus. So rays of light that is parallel to the principal axis, how will it go after refraction? It will go through F, and the one that goes through C will continue its path through C undeviated. If you extend it, we will get to a point where the two of them will meet, and that is where the final image will be. So this is an astronomical telescope that is producing a final image for us. astronomical telescope that is producing a final virtual image for us. There can be other instances where we will be asked to draw astronomical telescope in normal adjustment. If the astronomical telescope is going to be in normal adjustment, there's no problem with the position of the objective lens. What we will now have to adjust is the position of the eyepiece. We'll move the eyepiece as far back as possible. We'll move the eyepiece as far back as possible to ensure that its focal length or its principal focus exactly coincide with the principal focus of the objective. If that is the case, it means that we are going to be forming an image. If this is the f of the eyepiece, we are going to be forming an image that is at infinity. So when your initial object is at infinity and your final image is also at infinity, we say we have astronomical telescope in normal adjustment. Lenses can also be used to make things like lens camera. They can also be used to make slide projector. They can be used to make to correct defects in the eye. But to round up, we are going to take an example, probably on compound microscope. Don't forget that for compound microscope, there's a lens that is going to act on an object and it will form an initial magnified image. Then we have another lens, the eyepiece. This is the objective. This is the eyepiece. We have another lens that is now going to form a final virtual image of that object. Let's take a question. We are told that the image formed by an objective lens in a compound microscope is positioned at 4 centimeters from the eyepiece. This image formed by the objective lens is positioned at 4 centimeters from the eyepiece. The image of the objective is the object for the eyepiece. If the final image is at 25 centimeters from the eyepiece, if the final image is at 25 centimeters from the eyepiece, the final image is at 25 centimeters from the eyepiece. What is the focal length of the eyepiece? What is the focal length of the eyepiece? We want to find Fe of the eyepiece. We are given the object distance of the eyepiece. The object distance to the eyepiece is 4. We are given the image distance to the eyepiece, that is 25. But I'm going to write that as minus 25 because it is a virtual image. I can now find Fe. What will that be? I can easily do 1 all over Fe is equal to 1 all over Ue. E represents the eyepiece. It's still the lens formula that I'm writing. That's 1 all over F is equal to 1 all over U, that's 4, plus 1 all over V, that's minus 25. That's 1 all over F is equal to 1 all over 4 minus 1 all over 25. LCM 100. 100 divided by 4 is 25 times this 25 minus 100 divided by 25 is 4 times this is 4. So I will have 1 all over F is equal to 21 all over 100, and F must be equal to 100 all over 21. 100 all over 21 must be 4.8 centimeters. With that, we have come to the end of this very interesting topic. We hope you join us for our next class on sound. Thank you.